So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to be talking about chapter number 6 of our series of our book that we were proceeding on, and that is evaluating series. First of all, before you say anything, I'm just gonna say that to you that we are not gonna do chapter number 5. And the reason for this is, to be honest, I'm not sure about a lot of things in that chapter, and the second reason is that it's a prerequisite chapter, right? So it doesn't consist of a lot of things which are extremely important, and though you don't need to worry if you're thinking that it's a prerequisite chapter, then it must be done, it must should be done, right? But don't worry, I'm just gonna explain you everything in detail as much as I can, yeah, without just looking at that chapter, right? I don't hate that chapter, but yeah, I think it's that chapter is not that important. That's why I need to let's just skip that down, and let's just move to the next chapter. And please don't hate me. Yeah, I have just said everything honestly to you, and I'm not gonna lie here, right? Okay, so yeah, so basically what we have done so far here. Wait a second. Yeah, so firstly we have done our differential calculus, right? I have made a playlist as well, so you can consider checking out that as well. I would request you to just check that once. And then we have done integral calculus. Wait a second. And then we had moved on to Feynman's trick, and the fourth one was sums of simple series. And simultaneously I have made two videos, in which I have proved, the first one is this identity, that is sine of nx and sine to the n minus 2 of x dx. They basically generalized it, so it used to generalized as something sort of this. I hope you remember these things down. And the second one that I did today only, and I'm gonna upload it on, actually it's being uploaded here. Yeah, I'm just uploading it down, so it will be uploaded soon on my YouTube channel. That is the sum of tangent of x squared over n squared, and it is being generalized as pi over 4 minus arctangent of hyperbolic tangent of pi x over square root of 2 over tangent of pi x over square root of 2. So that's how, and yeah, I literally took 54 minutes to prove this down, and this one I have done in 25 minutes, and for this one I have taken 54 minutes. So yeah, this is kind of crazy because yeah, you will see in the proof of this one that I have used a tool for this to prove this down. So the tool was this identity, arctangent of theta can also be written as 1 over 2i times natural logarithm of 1 plus I theta over 1 minus I theta. So I have proved this identity as well in this very video, so I would just request you to watch all these things down once. So now let's just get back to evaluating series that we are here for actually. Okay, so now, okay, let's just get back to this. So we have most widely used series as the power series, or the power series taught in the introductory calculus courses. A classic example is, yeah, this one. It is basically, it's the you can say the infinite geometric sum. Geometric sum that we have studied in the previous chapter, right? Yeah. So basically, it's 1 over 1 minus x can also be represented as an infinite sum, infinite power sum, that is 1 plus x squared plus that as keeps going up to infinity. So basically, here from here you can say that this sum is equivalent to this kind of like expression, right? So this is extremely important, I would say, and I would just request you to just box it out and write this down if you haven't done that yet. And again, yeah, this part is when you just replace your x with, oh wait a second, like here in this, to get to reach up to there, what you have to do is to replace your x with minus x, right? So basically, that sum is so basically it's gonna be 1 over 1 plus x, and it's gonna be this sum as n goes from 0 to infinity of minus x to the n, and minus x to the n can also be written as minus 1 to the n and x to the n. So that's what it's just written over there. I hope you can just see that down. Yeah, so it's pretty easy to understand those things. And so basically 1 over 1 plus x can also be represented as the sum as n goes from 0 to infinity of minus 1 to the n times x to the n. Okay, and now what we have to do is we can differentiate both sides to obtain, yeah, we can take the differentiation. So basically we can differentiate both sides with respect to x here, and we can just differentiate it as well. So basically the differentiation of this part is gonna be, so basically it's just written over here, that is it's the derivative of x to the n, it's n times x to the n minus 1, right? Wait a second. Yeah, so basically that's what it's just written over here. We have n times minus 1 to the n, because minus 1 to the n is not depending on x, that's why we don't need to take the derivative of minus 1 to the n, but we have taken the derivative of x to the n, which comes out to be n times x to the n minus 1. And now we have to take the derivative of the left hand side as well. So basically when you take the derivative of this part, so though we have talked about that, but let me just tell you here. So basically the derivative of 1 over 1 plus x, you can write that down. What you have to do is you have to take the derivative of 1 plus x to the minus 1. So basically that's going to be giving us minus 1 times 1 plus x to the minus 1 minus 1. So it's minus 1 times 1 plus x to the minus 2, that can also be written as minus 1 over 1 plus x whole squared, right? So that's how it works. So here it is, and we have the sum. And now we can also integrate, yeah, we can integrate this down as well. So let me just remove this stuff here, and what we will be getting after integrating this with respect to x. So basically this is gonna be your sum as n goes from 0 to infinity of minus 1 to the n and x to the n plus 1 over n plus 1, and after integrating, it's just natural logarithm of x plus 1. So basically your infinite sum of natural logarithm of 1 plus x is coming out to be this sum as n goes from 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. Isn't that amazing? Yeah, it is. Yeah. Oh wait a second. Oh wait. Oh, actually actually he did took the integral of this very part here, and yeah, so that integrating that part, we would be just having this amount of thing. And the negative here, you might be thinking that what is this negative doing here? So basically when you integrate this, so it's like when you integrate 1 over 1 minus x dx, So basically after integrating it, you're gonna have minus of natural logarithm of 1 minus x. So that's how we can just multiply both sides with -1 to get rid of this one, and that's why we are having the minus as n goes from 0 to infinity of x to the n plus 1 over n plus 1. I need to just yeah, so I hope this is clear to you, right? And yeah, actually what we can do here, to reach up to here, from here what we can do is basically let n plus 1 equals z. So basically when your n is 0, your z is 1, so basically your sum is gonna be beginning from 1. So basically z is going from 1 to infinity, and when n is infinity, z is also infinity. It doesn't bother us, so it's x to the z over z minus. So that's how you can just, it's just in changing the variable, right? Yeah, that's how it works. And the way we just formulated this one as well, the way I have just showed it to you here, yeah, here it is, so you can just think of it. Yeah, so this is kind of easy to understand, right? But these are extremely important. Okay, and now it is vital to realize that these powerful tools have their limitations too. Oh, wait a second, I need to read this out. This is vital to realize these powerful tools have their limitations too. It is important to check whether these sums converge before proceeding and using, wait a second, yeah, before proceeding and using them on a specified interval. For example, only converges for the absolute value of x is less than 1, 6.1. So let's just get back to that. Yeah, I just forgot to tell you that, I'm sorry about that. So basically this converges when your absolute value of x is less than 1, and then only because if you might remember, so we have studied it in our geometric sum, infinite geometric sum actually. So for that case it was, you know what was infinite geometric sum? Yeah, so basically it was a over 1 minus r as sum as n goes from 0 to infinity of a times it was your r to the n, right? So that's how it worked, and basically we can just cancel out a both sides from here, and that's how we have 1 over 1 minus x as the sum as n goes from 0 to infinity of x to the n. And we have had known that the absolute value of r should be less than 1, so that's how it works. So yeah, it's pretty understood, I think. Yeah, it is. Okay, and yeah, okay, I got it. Evaluate this part. You know what, we have, let me just tell you something here. We have poly logarithmic function. Do you know, guys? Don't you? I'm not sure about whether you know this or not, but it's something sort of this. Li, wait, I'm sorry. Yeah, Li sub n of z. So basically it's this sum as k goes from 1 to infinity, I think. Yeah, and it's z to the k over n to the, no, k to the n. Yeah, it was k to the n. So basically it's a generalized form, right? And why I'm just telling you that right over here, because the sum that we are here, we are having a question here, we can just write this sum as a polylogarithmic function, and that's how gonna it work. Because, oh wait, oh I'm so sorry, no, it's not gonna work. Basically it's the reciprocal of this part. Okay, so it's not gonna work here. Okay, it's all right. But yeah, I have just told you that. I hope you can understand that, right? Okay, so the series converges by the ratio test. Okay, so basically in the previous chapter we have had the ratio test, but I'm sorry, I need to check that out once, but I'm sorry, I don't want to check that out actually. I haven't learned convergence a lot, but I will learn. and it doesn't mean that whatever I do is just waste. Okay, it's all right. I'm just being honest. Okay, I'm so sorry, just forgive me. But again, I'm in a learning phase, so just give me some time to learn uh, things, right? I'm not a master of it, so you just have to bear with me. Okay, it's all right, let's just get forward. And how did how did we reach up to here? Because so far what we have read is 1 over 1 minus x as the sum as n goes from 0 to n of x to the n, right? So basically what we're gonna do here is we're gonna change our index variable n as z plus 1. So when n is 0, your no, wait, oh, I think okay, wait, before that, let's just multiply both sides with x. So basically x over 1 minus x is gonna be the sum as n goes from 0 to infinity of x to the n plus 1, right? And now what we can do is we can replace n plus 1 with n only, and when n is 0, so basically when this n is 0, this n is gonna begin from 1. So that's how we can say that x over 1 minus x is sum as n goes from 1 to infinity of x to the n, right? So that's pretty important, I would say, right? You need to check whether the sum is going from 0 to infinity or 1 to infinity. Okay, and now differentiating both sides, so that's how it's gonna look. We can do that and multiply both sides with x, and we can differentiate and multiply by x again. So we have just differentiated it again, and we have multiplied with x, right? Okay, so basically if you might be thinking here, then let me just okay, yeah, I just got that. Okay, so that's basically it's the solution, and let's just dive into it once. So what we have done here, we have differentiated it, right? We have differentiated this part, and basically we have the product rule, right? Or the derivative of, wait a second guys, yeah, okay, so let's just talk about this in detail instead of just running. So we know that the quotient rule, don't we? The quotient rule of derivative, that says the derivative of two functions which are in like ratio of each other. So basically the derivative of the numerator times the denominator as it is minus the numerator as it is and the derivative of the denominator, and we have the denominator as it is whole squared, right? So basically for this case we have your f of x as, so basically this is your f of x and this part is your g of x, and we have the derivative of f of x is 1 and the derivative of g of x is minus 1. Yeah, I just got that. So basically when we just substitute them back here, so d over dx of x over 1 minus x, and the derivative of numerator, so it's 1 and it's minus 1 minus, and 1 times, oh wait, yeah, I'm sorry. Yeah, so the derivative of the numerator and 1 minus x here, and we have minus your, actually the derivative of the denominator is, so basically it's x, and we have 1 minus x whole squared, and from here we can say it's 1 over 1 minus x whole squared. So the derivative of x over 1 minus x is coming out to be 1 over 1 minus x whole squared. So there it is. right? And furthermore, we can just multiply both sides with x in order to just get rid of this n minus 1 here, and we can just proceed further here. And now we have to take the derivative of this part again. So basically from our previous encounter, we know that d over dx of f of x over g of x is f prime of x g of x minus, wait, I'm sorry, yeah, it's f of x times g prime of x over g of x whole squared. And again, the derivative of your, like, this is your f of x and this is your g of x. So basically again, your derivative of f of x is gonna be 1, and the derivative of g of x is gonna be 2 times minus of 1, and it's 1 minus x to the 3. I think it's perfect. Oh, I think I should just consider it writing something sort of this. It's d over dx of 1 minus x whole to the minus 2, which is minus 2 times minus 1 with the chain rule, and we have 1 minus x to the minus 3. So basically that's going to be giving us 2 over 1 minus x whole cubed, right? Okay, and what we have to do here again is, so basically let's just plug them back into our equation here. So what's that's gonna be giving us, let's just check this out. I think it's kind of getting big messy, isn't it? Okay, so the f plus x is 1, and we have g of x, which is 1 minus x whole squared, and minus your function as it is, and the derivative of it's 2 over 1 minus x whole cubed, and we have 1 minus x to the 4th. Wait, what is going on? This is being rude. Had I done something wrong? Oh, wait. I have done that. I need to check that out. I'm so sorry. So basically what we have to do here is we have to take the derivative of 1 minus x whole squared, right? So basically it's 2 times of minus 1 times 1 minus x whole cubed. No, it's not cubed. I think it's 1, because it's the derivative is gonna be minus 1. So it's gonna be 2 minus 1, which is 1. So it's minus 2 times 1 minus x to the, yeah, it's just x. Now let's just plug them back. So we have the derivative as, so we have 1 minus x whole squared and minus x times the derivative, it's minus 2 times 1 minus x over 1 minus x whole to the 4th. Actually, oh my goodness. So it's coming out to be, we have 1 minus x whole squared, and we have plus 2x times 1 minus x over, hey, wait a second, like, why am I having 1 minus x to the cubed? Wait a second, wait a dark second here. Let me just go through this, one more time here. Okay, yeah, I just got that. It's, so basically we can factor out 1 minus x from the numerator. So that's going to be giving us 1 minus x plus 2x minus 2x squared, right? And we have 1 minus x to the 4th, so we just got rid of these 4 and we would be having a cubed. And on the, wait a second, what am I having over there? I shouldn't be having that. 1 minus x, and we have 2x minus 2x squared. So basically Wait a second, I'm having 1 there, and why am I having 1? Um, not pretty much sure about this, but I need to just check this out. Oh my goodness. Oh my goodness, I have done something wrong here. And the thing is that I have taken the chain rule here, but I have considered this part as well, but I should haven't considered that one. Oh my goodness, it's just -2, because with the chain rule, the derivative of x minus x is just -1 that we have considered so far. So that's it. Am I right there? But still we are left 1 minus x 2 minus 1, which is just 1. Wait a second, because if it's -2, then we have, wait, yeah, I just got that. It's not gonna work like that. It's fine. It's perfectly fine now. And that's how we just got rid of this part, and we have this one, right? And we just got rid of this part as well. No, it's your 1 minus x. It's your 1 minus x here, I think. 1 minus x. Yeah. I'm so sorry again. I'm just messing up here. It's 1 minus x. Yeah, now it's perfectly fine. And we have just taken it common out. Like, we have just plugged out 1 minus x, a factor, from the numerator. So what we're gonna have here is 1 minus x plus 2x, and now it's perfectly fine. And in the numerator, we're gonna have 1 plus x over 1 minus x to the 3, and that what we have done here, we have just multiplied with x in order to get x to the n here. So I'm so sorry, I just messed up a lot of times there, but yeah, it's all right. We just got to learn something, right? Okay, now we have this sum. Let's just take a look at this part as well. So yeah, okay, so here we are gonna invoke some integrals. You know what, either you can solve a sum directly, or you can invoke integral of your integrand. So basically this like argument can also be written as this integral. Basically, when you integrate from 0 to 1/2 of x to the n minus 1 over n dx, so what you're gonna get back is 1 over 2 to the n times n squared. You can just check that out once, because it's pretty easy. It's 1 minus n, and we are having x to the n over n from 0 to 1 over 2, and that's gonna be giving us 1 over 2 to the n, and it's n squared. So yeah, it's pretty easy. And let's just see how this integral just made our life easier. Using the dominator convergence theorem, we can switch the order of integration and the summation to obtain. Yeah, sure, we can just switch it up. And from here, what we can observe that wait a second, we have this sum, x to the n minus 1 over n, as natural logarithm of 1 minus x over x. So basically I think, okay, it's minus as well. Yeah, we have just studied it previously in this video only, and now it's pretty easy to just talk about this integral. Either you can go, I think it's better way to just go with the di method, right? And you have to take the derivative of natural logarithm of 1 minus x and integrating 1 over x. So it's 1 over 1 minus x, and it's natural logarithm of x. So just take a look at this. This is how it's gonna work, and we are here. And now again we are gonna invoke an infinite sum using this very part that we have proved earlier, right? Now we have basically, when we just substitute this part, basically this very part right over here in the numerator of that integral. So it's gonna be looking like, this integral is gonna look like from 0 to 1 over 2 of, wait a second, I should have considered writing the denominator part first. And we have this sum as n goes from 0 to infinity of minus 1 to the n x minus 1 to the n plus 1 over n plus 1 dx. And furthermore, we can just switch up the order of the integration and the summation sign, and that's going to be giving us minus 1 to the n over n plus 1 integral from 0 to 1 over 2 of x minus 1 to the n dx, right? Okay, and so far we are having that much thing actually. So after evaluating this part, we would be having this very part actually, and we have this integral right over here, right? And we successfully did switch up the order of the integration, and we have just integrated this part actually. And that's what we can, that's where we can just separate, we can get two integrals separately, right? And this part is surprisingly Riemann zeta of 2, and that is being converged to pi squared over 6, and that is known as the Basel problem. And I have proved that down a couple of times, so you can just consider watching that. Okay, and we have considered this sum, oh wait a second, this very sum as s, and so basically that's what we are, oh wait, this is what we were here to prove down. Oh my goodness, just take a look at the beauty of this question, of this sum. So basically from here we have 2s as minus natural logarithm squared of 1 over 2 plus pi squared over 6, and from here we can isolate the s as pi squared over 6 minus natural logarithm squared of 2 or over 2. That's amazingly amazing, guys, literally. And just take a look at this question as well. We have example actually on question, f of n as the integral from 0 to 1 of natural logarithm of 1 minus x to the n over x dx, right? And what we have to do is to evaluate this very sum, that is the sum as n goes from 0 to infinity of f of n over n. So basically what we have to do is we have to evaluate this sum. It's 1 over n integral from 1 over 0 to 1 over 2 of natural logarithm of 1 minus x to the n over x dx. So that's what we are gonna evaluate here. And we have, okay, yeah, we have the expansion of natural logarithm of 1 minus x as minus times this sum as n goes from what, I'm sorry, as k goes from 1 to infinity of x to the k over k. And from here we can just substitute x, like we can replace we can just replace this x with x to the n in order to get an infinite sum that represent natural logarithm of 1 minus x to the n as minus this sum as k goes from 1 to infinity of x to the n to the k over k. So that's what we have done so far here. I hope you can understand that. And we have the denominator as x, and from here we have x to the n, oh wait, it's x to the n k minus 1 over k. And from here just interchanging and switching up the order, dominating convergence theorem, this interchanging the summation and integration to obtain this very integral. And this is kind of easily integrable because that's going to be giving you 1 over nk, right? Wait, yeah, so that's going to be giving you this k, and this k is going to be nk squared. So basically n is being constant here because our sum is being like indexed as k. So again, this part is your Riemann zeta of 2 that says pi squared over 6. So we have Riemann zeta of 2 over n. So basically your f of n is coming out to be Riemann zeta of 2 over n, and that's how you can just plug back the value of Riemann zeta of 2, that is pi squared over 6, to just get your f of n as minus pi squared over 6 times n, right? So that's amazing, right? Okay, and now we have a lot of questions that just plays around with the natural logarithm of 1 plus x and 1 minus x, like they're infinite sums. Okay, let's just move further on, and we have this kind of sum. Can I do something here? What can I do here is I cannot do anything, but it's 4n minus 1 minus 4n over 4n minus 1 minus your 4n and minus 4n plus, not minus 1, yeah, plus 1. Should we do that? I think we shouldn't do that at all, because that's gonna be giving us the same thing, get back to there. So instead of that, let's just use the Hamza-Alzamari stuff that he had done to evaluate that. So we have as like it's being expanded, something sort of this, and now this part can also be written as integral from 0 to 1 of x to the 4n minus 2 dx minus integral from 0 to 1 of x to the 4n minus 1 dx. And now we can just combine them both, and we can just have a combined integral, that is the integral from 0 to 1 of x to the 4n minus 2 minus x to the 4n minus 1 dx, right? And from here we can just look for our s as sum as n goes from 1 to infinity of integral from 0 to 1 of x to the 4n minus 2 plus 4n minus 1 dx. And again, switching up the order of the integration and the summation sign, so that's going to be giving us the integral from 0 to 1 of n minus like sum as n goes from 1 to infinity of x to the 4n minus 2 minus x to the 4n minus 1 dx. So basically we can just take a parenthesis in order to get to two different sums that we have done here. And next what? Okay, oh wait a second. So basically this is okay, wait, this, look at this sum. So it's this sum as n goes from 1 to infinity of x to the 4 whole to the n, and we have a factor of 1 over x squared. So basically this is your infinite geometric sum, and that can also be written as x to the 4 over 1 minus x to the 4. So yeah, it's just all these stuffs that we have studied in the very beginning of this chapter. But yeah, you just need to talk about where to use, when to use, and how to use. We have harmonic numbers. Oh wait a second, this is amazing. This is literally amazing. You know what the beauty of harmonic numbers is? When basically this is your harmonic number, right? So basically when you take the limit as n tends to infinity, so limit n tends to infinity of h sub n, and we have limit n tends to infinity of this very sum 1 over k, and we can just substitute n as infinity. So basically it's k goes from 1 to infinity of 1 over k, and this is, guess what, this is Riemann zeta of 1, not minus 1 but 1. And guess what, again it's diverges. So basically this the limit n tends to infinity of h sub n diverges to infinity. So you just have to take care about that. We have recall the harmonic numbers usually denoted as h sub n, right? And yeah, definition of the Euler's Mascheroni constant. Yeah, actually, we have a very well known definition of Euler's Mascheroni constant, which is being represented with the harmonic numbers. So that's amazing. So this is how you can represent an harmonic number as an integral as well. What you have to do is you just have to consider this integral, actually, and now you just have to take sum both sides. So basically taking sum as k goes from 1 to infinity, and so that's going to be giving us h sub k. I think it's not h sub k, but it's just h sub k. So that's what we have, h sub n as k goes. I'm sorry, I'm so sorry, it's h sub n, because when n is going, it's a finite sum, so h sub n. Great, so we have this part, and that's how you can just expand this as the geometric sum, right? So it's as the finite geometric sum. Actually, that's its notation for the finite geometric sum that we have studied in the previous chapter, in our previous video of this book. And now we have a couple of things, and now we have an amazing identity here that looks amazing. And yeah, and this identity is also important, guys. You need to check this out, right? You need to check this out. And I think I should just bring a proof video of this. I'm not sure, but yeah, it's kind of easy, but still I'll just try to come up with the proof of that. Actually, the proof of that is given right over here. You know what, let's just go through this once. You know what h sub n is? It's 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot dot dot. That just keeps going up to 1 over n. And now what can I do here is h sub n can also be written as 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot keeps going up to 1 plus 1 over n minus 1 plus 1 over n. And this very part can also be written as h sub n minus 1. So basically h sub n equals h sub n minus 1 plus 1 over n, and that's what it's just written over there, right? And now we can just subtract both sides with h sub n minus 1. So that's gonna be giving us this very equation. Okay, and now what we have to do is we just have to multiply both sides with x to the n, right? And we have to take infinite sums, that is sum from n equals 1 to infinity of this equation. So that's going to be giving us so basically taking this sum from n equals 1 to infinity. So the sum as n goes from 1 to infinity of h sub n times x to the n minus the sum as n goes from 1 to infinity of h sub n minus 1 times x to the n equals the sum as n goes from 1 to infinity of x to the n over n, right? And now what it is, it's basically minus natural logarithm of 1 minus x that we have studied in the very beginning of this chapter. Just recall that, right? So basically this can be written as something sort of that. And now we can just factor out an x here, and we can just write this as x to the n minus 1, right? And yeah, this part is right, because your n is going from 1 to infinity. That's why this part is right. This part is justifiable. And from here what we can do, because just take a look at this, because this part is right, so basically we can just replace this part with this part. So that's going to be giving us this sum as n goes from 1 to infinity of h sub n x to the n minus x times this sum as n goes from 1 to infinity of h sub n x to the n, right? So yeah, so basically we can just factor out this sum as n goes from 1 to infinity of h sub n x to the n. Wait a second. Yeah, So that's how we can have 1 minus x, and we can just divide both sides with that in order to get this final result. So that's pretty amazing. That's amazingly amazing. Okay, and now we have some problems on harmonic numbers. So these things are pretty much, I would say, not that difficult to just tackle, but yeah, we have this polynomial theorem. So this book is really amazing. This is very famous problem actually. But I think I should just yeah, we have to invoke double sums here. We need to just check that out once. Though I'm just looking for a separate video in which I should talk about those problems. And now we are at the very final edge of this chapter. We have this integral identity. Actually, it's given to use to look for this one. So that, yeah, that's amazing chapter. And now we have our next chapter as series and integrals, which we'll be doing in the next video. So for now, I think it's enough, guys. And again, guys, if you got to learn something out of it, please make sure to let us have and share. And yeah, I would say that sorry that I have made mistakes a lot, but it's all right. It's a part of learning, right? We have learned so far that it's a part of learning. So that's how we should make mistakes as much as we can, right? And for now, I would say goodbye. Just take care, love you, and just love your life, enjoy your life, love mathematics if you love it. Either just leave it. Yes, just find which is like, find that thing which is made for you, or you are made for that, right? Right. So yeah, that's how the life works. So we have 55, 56, 57, 58, 59. Thank you, goodbye, love you.